The next one we identified was compound systems. Compound systems are basically one system pulling on another system. We can identify that's a system pulling on another system by either kill points that can be evaluated as prusiks, knots, or fixed pulleys. Either of those applications where we're divvying out those systems. So for an example here, we're going to start with that compound 3, or that 3-to-1 that we've talked about, and we're going to talk about why I would consider that a compound system. Here's our change of direction pulley at the top. Here's our mechanical advantage pulley with a prusik or a progress capture device going to this primary line. Here's where our 3-to-1 component would be. If this were the pull, again, we would have that 1 unit coming in, that 1 unit coming out, resulting in 2 units at the prusik. That 1 unit would come up to the change of direction, come out of the change of direction, no math or summation at this point. That 1 unit comes down, catches that 2 units, and becomes that 3-to-1 mechanical advantage. If we were making this a more invasive compound system, and I'll talk about why I'm using that reference of invasive here in just a second, we would basically piggyback another system onto the back side of this. We could do that in any number of ways. So with this 3-to-1 coming out, if we were to put another change of direction pulley right here, run that rope back down, and apply another moving pulley right here, and clip that moving pulley into the same carabiner that's attached to this prusik, and run that system out, this just became a compound system. We've got one system that is pulling on another system. So if we analyze this through, here's what we're going to see. 1 unit of tension coming in, 1 unit of tension coming out, gives me 2 units of tension at this connection point. This connection point is moving, so I can visualize that as a kill point. That 1 unit of tension comes up and comes out, no math right here. 1 unit of tension coming into this pulley, 1 unit of tension coming out of that pulley, gives me 2 units of tension on this side of the prusik. Both of these carabiners coming out of these moving pulleys are attached to the same prusik. So we have 2 units and 2 units collected together on that prusik, progressing through that prusik, resulting in 4 units of tension here at the capture point. Coming back to what's coming out of that pulley, it's still 1 unit of tension above this prusik line. So we have 1 unit of tension coming up, 1 unit of tension coming out. That 1 unit captures that 4 units right there where they touch, and it results in a 5-to-1 mechanical advantage. A different looking variation of killing the system or piggybacking the system is to put midline knots within your system. So now imagine that 3-to-1 now comes up and has a knot put into it. That knot is killed at the rigging plate, and then we're going to come out of this knot with a 2-to-1 system and a Z-drag. Now, if we look at this, we can analyze our 1 unit of tension coming in, 1 unit of tension coming out. This pulley is moving with mechanical advantage, resulting in 2 units of tension at that prusik. As that 1 unit of tension comes up to this knot, however, this knot basically kills all that unit transfer coming through the system, and this leg of the rope will become slack until it hits the prusik. So it's unloaded. So we can't carry through that unit of tension through a midline knot. It's an important component when evaluating or counting units of tension. So this actually comes out of the knot as 0 units of tension. So 0 units of tension come down and capture that prusik where we had 2 units of tension, and it just correlates to 2 units of tension progressing through the system. We said that whatever comes into a pulley must come out of a pulley and stay the same until it hits a mechanical advantage component. So we have 2 units of tension coming into this pulley, 2 units of tension coming out of this pulley, resulting in 4 units of tension at this prusik. Those 2 units of tension travel up to the change of direction. They come out of the change of direction. Those 2 units come down and capture those 4 units, resulting in a 6-to-1 mechanical advantage. If you can identify those separation points within the system, then you can identify that this midline knot is a kill within the system, separating these two systems, resulting in a 2-to-1 system pulling on a 3-to-1 system. Another way to calculate mechanical advantage when you have compound systems like this is to multiply those mechanical advantages. So by counting units of tension all the way through the system, we were derived at 6-to-1. If I can look at this system very quickly and ascertain that it's a 2-to-1 pulling on a 3-to-1, then I can multiply the 3 times the 2, which will lead me to the same conclusion of a 6-to-1 mechanical advantage system. So anytime we've got a system pulling on another system and those pulleys are still traveling in the direction of the pull, it's going to be considered a compound system. The complex system is our last consideration. Complex systems are another one of those systems that may have some limited applications, because one of the primary concepts about a complex system is that typically the pulleys are moving in a direction towards one another. So the overall mechanical advantage system is collapsing from 2 ends. That makes it not a highly efficient system because it is in theory reducing our haul lane in half. If we've got a 40-foot haul lane where we typically could have hauled 40 feet before we had to do any significant resets, in this application we're only going to be able to haul 20 feet theoretically, because those directional pulleys will be collapsing from both ends. That's going to require more resets, which is going to slow down the overall rescue application. The advantage of complex systems is they can be very quick as mechanical advantage upgrades when you're converting from one system to another system. Additionally, they require less rope or less redirections of the rope to attain mechanical advantage, and less hardware and rigging components. So you'll typically see complex systems as very short, quick fixes for mechanical advantage upgrades, or in applications where rescue crews have maxed out their rescue cache and are becoming highly limited on either rope length or hardware for additional mechanical advantage rigging components. So here's an example of what a complex system would look like. Again, we'll start with that 3-to-1 concept. This is our change of direction pulley. Here's our mechanical advantage pulley with our progress capture, or our prusik. We're hauling. This would be our 3-to-1. If we wanted to convert this to a complex system, we could simply put in a pulley right here, attach a prusik to this portion of the haul lane coming out of the primary hub, and redirect the haul going the other direction. Now let's count our units of tension through this system, because we can see that we now have 2 pulleys working towards one another. So we now have 1 unit of tension coming into this pulley, 1 unit of tension coming out of this pulley. That's going to correlate to 2 units of tension traveling up this prusik. We have to do summation or addition at this pulley because this pulley is moving. Albeit the pulley is moving towards the load, but it's still a moving pulley giving us mechanical advantage. This 1 unit of tension travels down to this pulley. 1 unit in and 1 unit out results in 2 units of tension at this prusik at this point. That 1 unit of tension travels up, and remember the rule, what comes into a pulley comes out of a pulley and stays the same until it hits that mechanical advantage component. That mechanical advantage component being the prusik right here, that 1 unit comes up, hits those 2 units, and becomes 3 units. What goes in must come out. So 3 units in, 3 units out. No math here because it's a fixed anchor or fixed pulley at the anchor. Those 3 units of tension progress down until they hit the 2 units of tension at this prusik, resulting in a 5-to-1. So a 5-to-1 mechanical advantage, the ratios are the same, the force is the same, it's just collapsing in two different directions and required one less directional or rigging element than what would normally be required to build a traditional conceptual 5-to-1 application. Example of complex system, as well as the applications for complex systems. So, understand your simple, your compound, and your complex systems. Understand when you're going to piggyback and utilize those systems to maximize efficiency as well as ease of operation. Always try to use the smallest mechanical advantage as possible to accommodate the rescue and the rescuers. Try not to upgrade too fast, too quick, because obviously you're going to reduce the speed at which you can move that load. So don't always buy in for ease over speed of operation. Remember to let the victim drive the rescue. Contemplate the force that's going to be required to move that load. Think about the number of rescuers that are going to be required. Another important facet to consider is terrain and environment. So if it's snowy out, if it's wet out, if we're operating in slop or mud or very difficult footing-based haul lanes, that's another application where we may increase our mechanical advantage to afford what we're going to build to manipulate that load. That about summarizes the basic concepts or basic physics of mechanical advantage. And the most important facet is that your department or organization develop a systematic approach to mechanical advantage upgrades. You can train all personnel within the organization to do those upgrades so that it frees up your technical personnel to focus on more invasive areas or aspects of the rescue operation. Whether that's a 3-5-6-9 upgrade or a 3-5 complex 7-9, whatever avenue of approach it is that you decide to implement as an organization based on your equipment cache and the savviness of your rope rescue individuals as well as your organization, stick to it, practice it, and try to encourage all your personnel to understand units of tension so that when they build them, they can check them, they can analyze them, they can count through those units of tension and always ensure that their systems are built appropriately and safely.